Hello everyone, I am David Bernal, and today I'll be presenting about the Intractable Decathlon. This is part of the work done together with the IBM Quantum Optimization group. So as I was saying, my name is David Bernal Neira. I'm an assistant professor at Purdue University in their Davidson School of Chemical Engineering, and once again I'll be speaking about a recent paper that we put together with IBM Quantum Optimization group, and also giving some introduction to quantum optimization. So let's start on why do we optimize. I believe that we should start our conversation just by defining what optimization is. And to optimize is to search. To optimize is to explore. And this exploration is just on this quest for us to look for these optimal solutions. Later, I'll define them. But believe me when I say that this kind of search can be time-consuming, expensive, prone to errors. So the way that we tackle this is we like to take our real world and turn it into a model. We build these mathematical models that represent our understanding of them. They incorporate our assumptions and simplifications, and usually we balance the validity of these models and their tractability. So a useful paradigm is this thing called mathematical programming, where we write in terms of mathematical equations our objective, whatever defines what an optimal solution is or isn't, subject to certain constraints or rules that need to be satisfied while we answer the question of the optimization. And the answer itself, the values that can change throughout the search are called variables. So this is kind of the framework that we'll be working on. Now, when you wonder, okay, how do I build a model that represents our real world? It doesn't take long for you to identify that the real world is abrupt, unexpected, discontinuous, non-smooth, and a useful tool is whenever we take those mathematical programs and we assume that certain variables can only take discrete values. If that is the case, people call that integer programming or mixed integer programming in case that they are continuous and discrete variables. But this alone is a universal tool for modeling these discontinuities or non-convexities, we call them in optimization. And basically, this condition might arise from the fact that there are things that are indivisible. So if I'm optimizing a production schedule, then and I have indivisible batches, I don't know, because I'm producing hats or shoes, an optimal solution cannot be 3.7, right? But at the same time, and I would even argue more useful, we use these discrete variables, usually only at the 0, 1 level, or what we call binary variables, to encode logical conditions. Then the 0, 1s, they can start encoding yes, no decisions, up, down. And if you think about yourself this morning, you have already gone through a number of different decisions that involve binary choices. Do I go to the right or to the left? Do I brush my teeth or brush my hair first, right? So these kind of problems, they appear all over the place. So that's why I use the words ubiquitous, omnipresent. Anyway, once you keep digging deeper into how does our world look like, it's very, you notice very quickly that the world is nonlinear. So if we are going to build models that are going to represent our understanding of the world, they better be nonlinear as well. And certainly, sure, we can get around of these non-convexities only with the discreteness, but if you talk to your colleagues in physics and chemistry, in other areas of knowledge, and you ask them, okay, how do the equations that you have built look to describe whatever systems you're studying, they're usually nonlinear. So this kind of assumption that you can just write the objective or the constraints as a linear combination of your variables, it does not hold in general. So this leaves us with this kind of optimization problem, where we are minimizing an objective subject to constraints, and either the objective or the constraints can be nonlinear functions. And some of the variables need to take discrete values. So that is a quite general optimization framework. We call it discrete nonlinear, or later in the optimization community, people call it the mixed integer nonlinear program. kind of problem, and these are computationally hard. So let's visit them for a little while. Usually, if you are into optimization, you are more familiar into looking at optimization problems this way, where we present them with an objective function, this linear and nonlinear constraints and variables that can be discrete or continuous, and I just introduce a few symbols here. But more importantly, since I sit in a chemical engineering department, I need to keep motivating this kind of mathematical framework to my colleagues. So I very quickly go through various applications for chemical engineers of this kind of problem. So they go into designing new processes. We call that process flow sheet optimization. It goes into how to best operate those processes, and we call that planning or scheduling. We also do real-time operation of these systems. We call that controls, or we can even go all the way down to design molecules, so molecular structure encoding and so forth. Now, many of you are not chemical engineers, but that should not be an issue because the applications of this kind of mathematical framework, they go well, well beyond. So here I have a few more listed, some in medicine, some in other branches of engineering, civil engineering in this case. A very common application these days is in machine learning or data science, where you need to necessarily deal with nonlinearity in order to have like this universal learning schemes. Moreover, computational biology has been using this kind of techniques or network design. So all this to say that this is an extremely flexible modeling framework. So if you start wondering, okay, does this apply to my problem? The short answer is yes. And how can I be so sure? Well, basically because these kind of problems, they can encode Minsky recording machines, so basically any Turing machine, meaning that any computational problem can be built as one of these optimizations. So maybe you might wonder, okay, I've never used this tool before. I have been dealing with computational problems all along. How is it possible? And the short answer is that, sure, this is extremely useful to model phenomena, but once we have those models and we want to find those optimal solutions, we want to perform this search, we very quickly encounter a complexity issue. For those of you that might be familiar with computational complexity, these kind of problems, they belong to the NP-hard complexity class, meaning that verifying a solution can be done efficiently, finding one, the complexity grows exponentially with the size of the problem. So, and you can even prove that they become undecidable in certain cases. So how do we deal with this, right? I mean, we have this extremely powerful modeling framework that leads to problems that are very hard to solve. And you can go with a kind of naive approach. You can say, well, you know, the number of integer combinations is finite, so I might as well just find them all, evaluate each one of them, rank them according to their objective, and then choose either the first one or the last one, depending if I'm maximizing or minimizing, and I should be done, right? And although possible, this is extremely impractical. So this plot over here, in the horizontal axis, it just shows the size of some potential problems. In the vertical axis, it just has very large numbers. And the lines there, they correspond to the number of possible solutions that arise either from the simplest problem, which is that blue line, where the number of solutions will grow as 2 to the power of n, and more complicated problems, for example, routing problems. If you have ever heard about the traveling salesperson problem, the number of solutions corresponds like n factorial, and that's the yellow line. Just for context, the dashed lines, they correspond to very large numbers. So the blue one is the number of nanoseconds in a year. So if you had a computer able to compute one solution per nanosecond, it would take a whole year to just enumerate the solutions of a very tiny problem, right? And then you have the age of the universe in nanoseconds in the dashed black line. So basically, you'll run out of time in this universe before you're able to enumerate these problems. Or even worse, you run out of universe just because the number of atoms in the universe are fewer than the number of possible solutions to these optimization problems. So how do we solve this, right? I mean, this puts us in a situation where we really need to tackle these problems. And I would summarize our whole approaches as decomposition methods. We take a problem, we break it down in tinier pieces, hopefully that they are more easily solvable, and then we design algorithms to try to stitch those solutions together. Hopefully, each one of these sub-problems are solved with a method that is particularly well-suited for them, right? And then the load falls on the algorithm designer to come up with these methods to efficiently tackle these problems. And here is one example. So what are those problems, you might wonder? Short answer, easier problems. And easier problems, well, what does that mean? It could be continuous sub-problems, right? So whenever you're working with these optimization problems in the classical world, whenever you get rid of those discrete variables, the complexity lowers, right? You can apply gradient-based methods, for example. And for those, we have pretty good scaling. But surprisingly, in many cases, the sub-problems can also be discrete. And this is only a product of how good tools we have out there. So here I'm showing some numbers for IBM Cplex, which is a piece of classical code designed to solve this kind of discrete problems, and how much better it has gotten in the last 30, 35 years, right? And so if you start accounting how much better it got since 1991 up until 2024, and here I'm just drawing some raw numbers here, the total algorithmic speedup has been 3.5 million times. It's absolutely outstanding how far we have gone classically in addressing these kind of problems. Now, if you account for how much better computers have become, then you go into the academic literature, and there is people that are not concerned in saying that we have gotten 200 billion times better at solving these problems in the last 30, 35 years. So it's absolutely outstanding. And how? Well, I mean, there is a whole field in operations research, in discrete mathematics, in polyhedral theory that have advanced this field forward. So what have we learned so far? We have learned that classical methods, I haven't mentioned quantum so far, but classical methods are extraordinary, even when facing these problems, which are supposed to be, in their worst case, exponentially tough to solve. Now, how? Well, we usually use these decomposition techniques, right? And this requires from the algorithm designer to understand the structure of the problem, to know how this problem can be broken down into tiny pieces, and then using the right tool for the right task. And sort of spoiling the surprise ahead, if a new computational tool becomes available, then we should aim to find those substructures that we can take advantage of, and then we can integrate them into larger solution methods. So, nice to meet you. I'm David Bernal, so very briefly about me, I'm a chemical engineer, I'm a physicist, I did my PhD in chemical engineering, but my research topic was actually discrete nonlinear optimization. And after wrapping up my PhD, I spent a couple years working at the NASA Quantum and Artificial Intelligence Laboratory, where we were trying to evaluate how quantum computers could help for air and space exploration. After that, I went back to my roots in academia and in chemical engineering, and I joined Purdue, where basically I have been putting together this amazing group of individuals. My team is called Sequoia. It stands for Systems Engineering via Classical and Quantum Optimization for industrial applications. It's also a beautiful tree that grows on the west coast of the US. And we have been sort of translating that mission of the NASA Quantum AI Lab into chemical engineering. How can we use quantum computers to address problems in chemical engineering? So before that, we had some experience with these classical methods. We actually had spent a lot of time benchmarking them, meaning we go and evaluate empirically how these codes behave, and we basically understand how far or close are to working with practical problems. I'm a very practical man. I like to address problems that you face in reality. And these worst case complexity results, for sure, they are important, and we incorporate them into our algorithmic design. But at the end of the day, we argue that a problem is truly solved whenever you can solve it for real. Now, to keep pushing the boundary, we have been coming up with both theoretical and algorithmic improvements and implementations out there. So we have been working on different software for this. So, and what have we been using it for? And certainly, I hope that this serves as inspiration for those in the audience. Remember, I'm a chemical engineer, so I care about distributed manufacturing. I care about distillation columns. I care about refinery operation, maintenance, and all these problems, at the end of the day, we have been able to shape them into these discrete nonlinear optimizations and then apply the right tool for the right task. So anyway, enough about me, right? Let's talk about quantum computing. So certainly optimization problems appear all over the place. And many of these problems, as I was mentioning before, they belong to this NP complexity class. And let's start with the bad news. A quantum computer will not help you solve NP problems in polynomial time, unless P equals NP, and then we have a whole clash of the hierarchy, of the complexity hierarchy. But basically what this is telling us is that we need to use quantum computers in the context of NP optimization problems the same way that we have been using classical computers, meaning we will use them as powerful heuristics that are bounded in performance, but then it's a matter of algorithm design, algorithm engineering, so to say, to push the boundary forward. So, and this is pretty much what I mentioned here, right? Certainly, quantum computing can provide these speed-ups at the asymptotic level, right, for certain optimization problems. It's very hard to predict when this is going to happen. So maybe the approach should be an empirical one, where we go, run the problems, try to evaluate how they work. And certainly, the second phrase there can be a little bit controversial for this audience, but no quantum advantage has been found for practical optimization yet. And certainly, folks in the audience might come back to me and be like, oh, we have this latest result and so forth. That's why I include that tiny asterisk there, because I would be among the happiest people if this statement was not true. Anyway, so practical and heuristic speedups are of interest. Certainly, the picture in the complexity diagram there is kind of a simplistic one. Much more recently, in the IBM Quantum Optimization group and their review published in Nature for this particular case, these whole complexity classes have been worked out a little bit better. Anyway, so if we express our optimization problems as mathematical programs, that's what I was saying at the very beginning, where we had in terms of equations, our objectives and constraints and variables, and you start classifying them according to the nature of the constraints and the nature of the variables, whether the constraints are linear or nonlinear, or the variables are discrete or continuous, you end up with a map like this. And you might see that there are two areas that are highlighted and that I want to talk about. Then on the bright yellow area, we have what people call convex problems. Among them, linear programs, semi-definite programs, and for them, there have already been algorithms proposed to be run on fault-tolerant devices. And these algorithms, they actually come together with performance guarantees. So it's a very exciting field. I certainly recommend everyone to look into that. But our current devices are not there yet for us to implement this kind of methods. The other area, the light blue there, is heuristic or approximate methods for discrete optimization. And here, once again, I am not going to claim that we will be able to solve these problems exponentially faster, right? But I can claim, though, that if you know nothing about your problem, and you just do, let's say, the brute force enumeration of the solutions, you can do it quadratically faster with a quantum computer, if you, for example, use Grover search. So certainly, these two bounds define like the field that we have to play with. And certainly, if I now go and sit down and understand the problem that I'm dealing with, I can exploit that structure and hopefully get to some better solution that we currently have. So, and why QAOA? Why this quadratic, unconstrained binary optimization? Well, for the physicist in the audience, this is equivalent to the transfer field Ising model. So, and we like that from a physics standpoint and from a hardware standpoint even, because then we can use these kind of methods. Okay, so how do you do this optimization? And I'm gonna use this beautiful image that I found in the archive the other day to try to convey this message on how this optimization happens. The green surface there is gonna be a cartoon of our optimization problem, okay? And what we want to do is to find the lowest point on that green surface, on that green landscape. And the point, that red bead that is there, the position of that red bead is going to be the value of our variables. So usually in classical optimization, we have methods that try to move that bead. How? Well, it depends on the algorithm, whether you follow the steepest descent direction and whatnot. Usually you can have that bead move to the lowest point. Okay. Now, on the right-hand side, you have this purple shape. And that purple shape represents another optimization problem. I would argue a harder optimization problem than the green one, because that one has more ridges. If you're an optimizer, that one has more local optima. So finding the lowest point is going to be more challenging. And certainly, if I just try to push that red bead, I might get stuck in some of those valleys without finding the lowest point. Now, the principle that we're going to use here is the following. Assume that I start with the green landscape. I allow quantum interactions to happen on this system, and then I very, very slowly start transforming the green landscape into the purple landscape. Okay? The red bead is just going to follow some path, but I am not directly influencing it. It's just following this path. And once I finish that, let's call it evolution, I go open the box, check where my red bead is, and if I happen to have started in the best solution of the green landscape, I am guaranteed to be at the best solution of the purple landscape. This is absolutely outstanding because it's almost like as if nature was solving your optimization problem. And this, certainly, you can prove it out of basically properties of Schrodinger evolution, and people call this the quantum adiabatic algorithm. So just to list it out, you have this adiabatic or very, very slow evolution, right? And certainly without many interactions with the surrounding universe. You start at a problem, the green one, that is easy to describe, easy to solve, something that you can even know the solution ahead of time. And then you evolve that onto the purple shape. Hopefully that purple shape corresponds to a problem that you care about solving, that you don't know the solution of yet. And once you perform this evolution, then this is a way of finding a solution to the purple shape. So if you're able to map your problem onto that purple shape, then you're done, right? I mean, nature is solving this problem for you. Obviously, this is a theoretical, idealistic algorithm. This adiabatic evolution would require basically evolution at 0 Kelvin. And you can try very hard, and maybe you have heard about quantum annealers. That's what they try to do. They have this physical implementation of this algorithm, which, unfortunately, because we cannot get to those idealistic conditions, break the convergence guarantees, meaning that we cannot guarantee that we'll find the optimal solution. It doesn't matter. It's still a heuristic method from the optimization perspective. And although you're here, right, I suppose that you care about quantum, but assuming you don't, there are a number of other solvers that don't rely on quantum that can still tackle these so-called problems. And people call them Ising solvers or Ising solvers, okay? Cool. So, but let's assume you want to use IBM's computers, right? You want to use a gate-based NISQ device. And I have good news for you, and if you were here yesterday, you might have seen the whole tutorial where people were talking about this QAOA algorithm, the Quantum Approximate Optimization Algorithm, Quantum Alternating Optimization Ansatz, depending on how you read the literature. But basically, what a way of understanding this algorithm is a discretization of this smooth, slow path between solution green and solution purple, okay? And this one is even more interesting because then you can do a little bit of theory and prove that it has something called approximation bounds. For very well-structured problems, you know that the solution that you will obtain will be within a given percentage of the global optimal solution without spending exponential amount of resources. So this is very exciting. And now, what about the future? Well, the future is still open, right? When we reach the era of fault-tolerant quantum computers, there are also a battery of algorithms ready to be implemented to tackle this kind of problems. So it's kind of a nice framework to pose optimization, at least discrete optimization, okay? So now the issue is, okay, how do I take those problems that I started this whole talk about, these discrete nonlinear optimization problems, and transform them into these QAOAs or Ising models? And certainly some people have already been doing some work about it, right? And you can see, if you know what CARPS 21 and P-complete problems are, you know what they are, right? But they have already been mapped onto Ising. Or you can also do reformulations. This is what we call in classical optimization when you turn a problem into another, hopefully without changing what its optimal solution looks like. And the steps are kind of easy, right? I mean, originally, let's assume that you had continuous variables, you turn them into integers. How? By discretizing them. Now you have integer variables, you turn them into binaries. And we know how to binarize integers for the longest time. Now, if you have a nonlinear equation in terms of binaries, you can use something called pseudo-Boolean optimization to turn that into quadratics. And once you have quadratics, the only thing remaining is that you might have constraints. And those constraints, they need to be basically moved onto the objective to end up with an unconstrained problem. So there are these 4 steps, certainly easy to describe, not so trivial to implement. And for that, my lab has released this open source package, QAOA.jl. It's a Julia package that basically takes your problem, if you model it using the Julia language and the JUMP algebraic modeling language, and turns it into those QAOAs automatically for you. So if you are an optimization practitioner, such as me, and you have your different applications, are they in chemical engineering, are they in other domains, and you want to try this kind of quantum solvers, then in a single click, you should be able to transform them. So here is a little bit of details of what we're able to do. So we're able to transform a number of different constraints. And not only that, once you have those QAOAs, we also build interfaces to send them to your favorite Ising solver. Whereas whether it's classical, and then we have parallel tempering, some code that we developed at NASA called PISA, or whether you want to use quantum annealing, and we have some interfaces for that, or even if you want to use QAOA on IBM devices, right? So we are able to connect through Qiskit directly there, okay? And finally, we have some library of instances. In case that you don't have your own problems, don't worry, we have 6,000 for you to be able to solve for us. Anyway, so let's see this quick example. How do you get to solve a problem with IBM hardware from Julia, right? And the way that we do it is in a single line of code, and let me point here, right? You have you define, let's say we want to use QAOA, you define a tiny model, you define this using the syntax of optimization, and then inside of this optimized model, the whole magic is happening. We take that problem, we reformulate it if necessary, then we send it over the internet, we retrieve the solutions and put it back into your computer, right? And I am very proud to say that actually this is the fastest tool out there. How can I say? Well, we benchmarked it, right? We went out there and tried to reformulate a number of different traveling salesperson problems. So here you see in the horizontal axis the number of variables that problem has, and how long would it take for us to take that problem and turn it into a QAOA. And other competing tools, they notice that this axis is logarithmic, right? So certainly if we can do, for example, 10,000 cities in less than 10 seconds, other tools, we were a little bit impatient and just finished the computation after a few hundreds of seconds. And this is not only for the TSP problem, for the number partitioning problem, we have similar results. So we're pretty excited about this. It's fully open source, so feel free to use it. Now, benchmarking, right? I mean, that was in the title of my talk. That's kind of the purpose of this presentation. So I use most of my time just giving you the background, but it will all fall into place once I wrap this up. We are in this business of quantum computing, right? We are designing quantum algorithms, and certainly one of the most important questions that we ask is this better than classical, right? And then how do you answer that question? Well, there are different ways of answering that. You can go and try to do some mathematical proofs, right? And you can actually prove that in certain cases, you have this provable quantum speedup. Now, with respect, obviously, to the classical, in some cases, the classical algorithm developers are not done, right? So even if we are able to prove that our quantum algorithm is better than whatever is out there from the classical standpoint, we cannot disprove the fact that somebody might come up with a better classical algorithm. And that's the case for Shor's algorithm. Nobody has been able to come up with a classical prime factorization algorithm, but who knows, right? I mean, maybe they will. Now, and finally, let's focus on this observed quantum speedup. We want to look into problems, in practice. Once again, I'm a practical man. I care about solving this problem. So optimization, once again, they pose a challenge for this kind of speed-up analysis because many of these results are kind of hard considering the complexity class of the problems that we're dealing with. So, but I hope to convince you that this should not discourage us from trying to look into these applications. We want to get this problem solved as efficiently as possible because, like society depends on them. And there are so many applications out there that would greatly benefit from us being able to tackle these problems more efficiently. So finally, speedups should be observed at the application scale of the problem of interest. And in order to verify that, well, we might as well just solve the problem. Just treat it as an experiment and see how well it performs. So here we get to the paper. Right? So this is the Quantum Optimization Benchmarking Library. And this was a beautiful international collaboration. This is just the list of authors, right? So certainly people from the Zuse Institute in Berlin, led by IBM Quantum Optimization folks. There are 3 sequoias in this group, right? So 2 of my students and myself, we contributed to this. And basically here is the abstract of the paper. If you feel like reading it, you can scan this code and then you can go into the paper. But together with the paper, we also put out a library. So the paper, the contribution is that we went out there and identified 10 really hard problems, but really hard for everything we know. Every single classical method that has been tried to apply on them struggles to find solutions to them. So if we are going to claim in quantum optimization that we are better than our competition, well, we might as well just solve these problems and not trivial problems, right? I mean, sure, we have to start somewhere, but this is the end goal. If we're able to solve these problems, then I would claim that we're done. So let's keep going. We went out there and started asking questions such as, okay, what are the goals of benchmarking? And we have this very nice discussion in the paper, which was a result of a discussion among all this group of co-authors. We identified 3 kinds of benchmarking. So the first one is applications benchmarking. You have a problem and you want to use the tool that best solves it. And that might even allow you to have some freedom on how do you represent this problem. And certainly my group has been working on this, and I want to shout out some previous work that we have done with the Quantum Economic Development Consortium, where we started with these application-driven benchmarks. Now, on the other side, there is this algorithmic benchmarking. You want to check whether an algorithm can be improved and maybe moving some switches inside of that algorithm, and that's how you get recently we put out this paper. We call it the window sticker informally, but formally it's called a stochastic benchmarking library. And by understanding this kind of solvers, their probabilistic nature as a stochastic process and sampling out of them, then we can come up with, let's say, disciplined ways of understanding how their performance work. Finally, you can argue, let's do system benchmarking, right? And every time IBM releases a new quantum computer, there are benchmarks that want to answer, okay, is this better than the previous generation? And certainly, this is also something else that we have been working here with a few other co-authors in this audience on figuring out the progress of these quantum computers. They have been becoming better and better as time progresses, and we like to track that. So certainly, this paper focuses on the application benchmarking, okay? So we had a number of metrics, right? Let's run these problems, try to compute how much effort or how many resources we throw into them, what's the kind of solution that we get out of it, and how long did it take to solve the problem. I hope we can all agree that those are reasonable things to keep track of. And then we created like this kind of formatting that is both in the paper and in the library. So later we'll see this is a challenge to the community, to all of you, to try to solve these problems more efficiently. So whenever you claim that you have, whether classically, quantumly, with a hybrid method, well, you need to tell us how you did it, right? This is how we keep track of how science makes progress. So we have some metadata, some solution quality, modeling details, algorithmic details, and on the back end, we can compute the resources once we start summing up the runtimes. Okay, so yeah, certainly for difficult instances, we focus mainly on solution quality because many of the problems that we put out there are unsolved. They are still resisting best solutions from the classical or the quantum community. So if you want to be famous and put your name close to one of these problems, well, be my guest. So which are the problems? We have market split, we have independent set. I bring those two up first because they're part of the IBM Quantum Challenge this year. But we also have this one, low autocorrelation binary sequences. We have something called the minimum Birchhoff decomposition, some applications in sports scheduling, some applications in routing, so vehicle routing problem, portfolio optimization, the Steiner tree instance, and you can go in detail in the paper and check each one of these instances. We kind of classified them in 3 families, so some of them have been extremely well studied before the 2000s. Really strong classical contenders have come up. They are still unsolved. Now, we have limited attention received, also because these problems can be new. And finally, some practice-inspired problems, right? Portfolio optimization, routing problems, we can all agree that they are very practical. So we go and do the usual classification. We get some numbers out of them. And here you can see when we plot these problems, so in the horizontal axis is the size of the problem that we're dealing with, and in the vertical axis there is a metric of the density, basically how many constraints against how many variables we have. We can put all of our problems here. So you can see each one of the colors corresponds to each one of the families of the problems. I would like to draw your attention to this tiny plot. It's exactly the same axis as above, but now the colors, they correspond whether we, as humans, have been able to find an optimal guaranteed solution to those problems or not. And believe it or not, all these purple ones are unsolved. We have not been able to solve them yet. Okay, so we also transform them into QAOAs, right? Just now you know why, right? Because we want to eventually maybe make use of these quantum algorithms for them. And allow me to show you just in the last minute that I have an example. We have maximum independence set. I chose this one because it's also part of the challenge this year. And in the paper, we respond, okay, what is this problem? Why is it interesting? So basically, you have a graph, so you have some nodes and are connected to each other, and you would like to find the largest independent set of this graph, right? And there are QAOA reformulations for this and whatnot. So non-adjacent vertices in a graph, we want to find those 2 sets, the largest independent set. And this is an NP complete problem. We go and we try to solve them with as many classical methods as we could, such that we could tell people, okay, this is where the state of the art lies, we need to make this better. And finally, we get all these results. And last but not least, for this one, we were able to capture some of the quantum computing time. And so we tried to solve them, in this case, using QAOA with the QBO model on IBM FES. Hopefully, as part of the challenge, you will be able to beat these results that were obtained back then and to put your name into the library, right? So time is up. What have we learned? We've learned a few things. So in the fault tolerance regime, we certainly need to improve software and hardware to run quantum circuits faster and with fewer errors. And this leads to a path to quantum advantage. Now, the quantum algorithms designed for discrete optimization are limited right now in terms of problem class, in terms of problem sizes, in terms of convergence guarantees. And we need to think about them of cool and potentially efficient heuristics. But that's good enough, right? I mean, if we are able to push whichever problem can be solved in practice, then we can start tackling so many other applications. So the goal here is for us to develop new and better quantum algorithms and investigate these new optimization models. And finally, these existing models and algorithms are closely aligned with this classical method. So maybe we need to start thinking a little bit out of the box and explore these new possibilities. So with that, I thank you for your attention, and I look forward to future interactions. Thank you.